Hey guys. So in this question, you have a particle of mass m and charge q attached to a light insulating thread of length L. The other end of the thread is secured at point O. So you have this particle attached to this thread which is secured at this point. Exactly below this point O, you have a small ball having charge capital Q, which is fixed on this horizontal surface. The particle remains in equilibrium vertically with the string being taut. So at this position, it's mentioned that this particle is in equilibrium. The distance of the ball from point O is also given as L. So the distance of this ball from point is also given as L over here. So the question over here is find the minimum value of capital Q for which this particle will be in a stable equilibrium for any gentle horizontal push given to it, right? So when this particle Q is being displaced from its equilibrium position, we have to ensure that it's remaining in stable equilibrium, right? So I've drawn the diagram already. I've displaced small q by an angle theta from its equilibrium position right now, right? Okay, so we know the conditions for stable equilibrium. We say a particle is in stable equilibrium that, when displaced by an angle theta. It when displaced from its equilibrium position, it has a tendency to come back to its equilibrium position over here. So that's the idea we'll also be trying to use in this question. We'll after displacing this particle by an angle theta as shown over here, we'll look at all the forces acting on it and we'll ensure that the net force is acting towards the equilibrium position, right? Or in this case, since it's moving in circular motion right now because the string is taut, we'll make sure that the tangential force is acting towards the right. Is the idea we'll try to apply in this question, right? Okay, so what are the forces acting on this particle? The forces acting on this particle are mg and your electrostatic force of repulsion. So let me try to draw a diagram for that. You have your electrostatic force of repulsion acting along the line joining them. So electrostatic force of repulsion will be acting this way. And your mg force will be acting in the downward direction, right? So now our idea will be we'll try to take components of these forces along the tangent right now. We'll try to take components of these forces along the tangent and we'll ensure that this net force is towards the equilibrium position. Okay, so let me draw a better diagram in order to look at the geometry of this question. So let me exaggerate this diagram a bit. So this was your string. This was your point charge Q, which is located below point O. This is your small q. Which has a mass m as well, right? So mg force is acting this way. Electrostatic force of repulsion is acting in this direction, right? We can write the values later, but let's first figure out the components of these forces acting along the tangent. So this will be your tangent. It should be perpendicular to this radius. So this will be acting this way. So we need to find components of these forces along this tangent. Okay, so this angle was theta. So this angle will also be equal to theta. So component of mg acting along the tangent will be equal to mg sine theta. And this component of mg is acting away from the equilibrium position, right? Okay, now we need to find the component of f which is acting along the tangent, right? So let me again, f was acting along this line, whereas your string is acting along this line. So what we need to calculate is this angle, which will be equal to this angle itself. So this angle is 180 minus theta. And because both these lengths are L, both these angles have to be equal. So this angle has to be equal to theta by 2. So this angle will also be equal to theta by 2, which means your component of force acting along this direction will be equal to f sine of theta by 2. Right? Now our condition is straightforward. We just need to ensure that f sine of theta by 2 has to be greater than mg sine theta. And this is where we make use of this condition that is given a gentle horizontal push. So your theta is a small angle. So we can write this as f into theta by 2 should be greater than mg into theta. So we get the condition that f has to be greater than 2mg. F has to be greater than 2mg over here, right? Okay, then now let's write the expression for what the force will be at that new position. So your force between these two particles will be equal to, given by Coulomb's law, that is equal to kq by r squared, where r is this distance. And how do I find out the value of r? We'll now find out the value of r by using your properties of triangle. That is, I'll write r by sine of 180 minus theta is equal to L by sine of theta by 2. So from this you get R is equal to L into sine of 180 minus theta, which is sine theta itself, by sine of theta by 2. So this will become equal to 2L cos of theta by 2. But because once again theta is a small angle, we can conclude that R is equal to just 2L itself, as cos theta will be tending towards 1. So we'll be approximating R to be equal to 2L over here. So we'll get the force value to be equal to KQQ divided by 4L squared. Right? And now trying to plug them in this condition. So you want F to be greater than 2 mg. So because we want F to be greater than 2 mg, we'll write KQQ by 4L squared has to be greater than 2 mg. So what should your value of capital Q be? Your value of capital Q has to be greater than 8 mg L squared divided by K small q. So that implies your capital Q value has to be greater than 32 pi epsilon naught mg L squared divided by small q. So your minimum value of charge required then will be equal to 32 pi epsilon naught mg L squared divided by q, right? So hopefully this question was proved useful to you. I'll see you guys in the next video.